Hello everyone and welcome to our Calc notes for section 6.4. Today we're going to be talking about arc length and then surfaces of revolution. So first, we need to deal with arc length. And if we're going to do this, we need to have something called a rectifiable curve. And this is one that has a finite arc length. And for this to happen, the curve has to be continuously differentiable and smooth. Okay, so what we're going to do is we're going to transform the distance formula into the arc length formula. Okay, so let's just say on this curve we wanted to find the length from here all the way to here. So the interval that we're looking for would be from A over to B. So we're going to take a very calculus-like approach here. And to find the length, we're actually going to take approximation. If we split this into a couple different points here, we could find the distance in a straight line between these points. Okay, and we can find the length of a straight line because of the distance formula. So what we have here is we split this up into three regions. And we'll just call this x sub naught, or x sub 0, x sub 1, x sub 2, and really this is going to be x sub n, okay, because we could have n sub-intervals on here. So when we think about this, this would be the point x sub 0, y sub 0. And this one would be the point x sub 1, y sub 1. This would be x sub 2, y sub 2, all the way up to x sub n and y sub n. Okay, now that we have our picture drawn, we can kind of see what we're doing. We're going to find the sum of all of those lengths right there. So let me just write the distance formula here. So you'll recall that it's the square root of x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. And that comes from the Pythagorean theorem. Now, what we're trying to do, because we have lots of segment lengths here, we're going to add them all up. And so we're going to change the D into an S. And the sum of all of these, we're going to use our summation notation. It's going to be the sum from I equals 1 to n of all of our lengths. Now, when we look here at x sub 2 minus x sub 1, that's really just the difference in the x values. And we're going to call this delta x sub I, so whichever interval we're talking about. And then that's still squared. And then plus, well, if we have y sub 2 minus y sub 1, that's just the difference in the y's. And so we're going to make this delta y sub I, okay, for any interval there. And that's going to be squared. Now the next step we're going to do is not necessarily intuitive. So we're going to extend this square root here, and we're going to multiply delta y sub I squared by delta x sub I squared over delta x sub I squared. So we're really multiplying by 1. We don't change the value there at all, but you're going to see in a minute why we do this. Rewrite this here. So nothing happens to our delta x sub I squared. And here what we're going to do is move the delta x sub I squared under the delta y sub I squared. So we get delta y sub I squared over delta x sub I squared. And then we still have times delta x sub I squared. Okay, so in our next step, we're going to do a couple of things. We still have our sum. We still have our big square root. What we're going to do is factor out a delta x sub I squared. And then we're going to rewrite this, okay, as delta y sub I over delta x sub I squared. If we factor out a delta x sub I squared, we're going to get a 1 here, and then plus delta y sub I over delta x sub I, and that's going to be squared there. And this is still times delta x sub I squared. And now because we have this multiplication of the delta x sub I squared, we can actually take the square root of that. And we're going to be left with our sum of I equals 1 to n of the square root of 1 plus delta y sub I over delta x sub I squared times delta x sub I. Now at this point there's a couple really important things to notice. If we have delta y sub I over delta x sub I, that's the change in y over the change in x, which we also know is the slope of a line. And the slope of a line in calculus is also the derivative. So delta y sub I over delta x sub I is f prime of x. Right? It's the dy over dx. So that's f prime of x. And then this part right here, delta x sub I is just the change in x, and this is just going to be dx in calculus. So we make one more jump now till we get to our formula for arc length. Okay, so continuing our formula, S is going to be the limit as our partitions go to 0 of our sum from I equals 1 to n of the square root of 1 plus f prime, and we're not going to use x, we're actually going to use c sub I squared times delta x sub I. So c sub I, remember, was just any point on this interval. Okay, and now if we take that limit as the partition goes to 0, we're going to get S equals the definite integral from a to b of the square root of 1 plus f prime of x, or the derivative of x, squared with respect to x. And so there is your arc length formula. One other note here, if we're talking about functions of y, so if we're looking at something that's in g of y, the arc length is going to be the definite integral from the bottom to the top, the square root of 1 plus g prime of y squared dy. So this works also if you have functions of y as well. So let's go ahead and try an example here. Okay, so it says find the arc length of the curve on the given interval. So here we have the curve x cubed over 6 plus 1 over 2x on the interval from 1/2 to 2. So here is 1/2 going all the way up to 2. So here is the arc length that we're looking for. And the first thing we have to do in these problems is find the derivative of the function. So y prime here, oh, we got to think back to derivatives. So this is going to be 3 times x squared over 6, and then plus, let's see, 1 over 2x. So that's really x to the negative 1. So we're going to get negative 1 over 2 and then x squared. And we can rewrite this as x squared over 2 minus 1 over 2x squared. Okay, so that's always your first step, is to find the derivative of the function. Now we can go ahead and find the arc length. So s is going to equal the definite integral, well, from 1/2 to 2 of the square root of 1 plus that derivative squared and then dx. Alright, so from here you can type this into your calculator to get your answer, and you should get s equals 2.0625. Alright, so using both our derivative and our integral, we can actually find the length along a rectifiable curve, so a continuously differentiable and smooth curve. And so I know that length is 2.0625. Pretty cool, huh? Alright, so let's try our next example. Here we have the curve y minus 1 cubed equals x squared. And we want to find this on the interval from 0 to 8. So we're going to go from 0 all the way up to 8. So we're going to try to find this length right there. Okay, so this function is not either a function of y or a function of x right now, and so we're going to have to alter it before we can actually take our derivative. So we can either solve for y or we can solve for x. And let's just go ahead and solve for x in this case, just so that I can show you this other arc length formula right here. So here, to solve for x, all we'd have to do is take the square root of both sides. And so then we'd be left with x equals, well, the square root of a cube. This is just going to be y minus 1 to the 3/2. Okay, so it wasn't too bad. And now here we have our function of y. Okay, so let's go ahead and get x prime now. So it's just going to be 3/2 times y minus 1 to the, well, 3/2 minus 1, which is just 1/2. Okay, which we can write as 3 times the square root of y minus 1 over 2. Okay, so now if we're looking for arc length, s is going to be the integral from the bottom to the top. So the bottom over here is going to be at y equals 1, and then the top is going to be at y equals 5. So s is going to be our definite integral from 1 to 5 of the square root of 1 plus, now, x prime squared, so 3 times the square root of y minus 1 over 2 squared, and in this case, with respect to y, so dy right there. Alright, and if we plug this into our calculator, we get s equals 9.073. Alright, moving on. I want you to try letter C on your own here. Go ahead and pause the video and then come on back to check your work when you're done. Alright, welcome back. So if we want to take the derivative of natural log of u, remember that's just going to be u prime over u. So we let u equal cosine of x right there. And so u prime is negative sine x. And so y prime here is going to be negative sine x over cosine x. And it's just easier if you write this as one function, which would be negative tangent x. And then here you can see your integration formula for arc length. And you should have gotten 0.881. Right, we're going to try one more example together. And we have a little word problem here. So it says an electric cable is hung between two towers that are 200 feet apart. And the cable takes the shape of a catenary whose equation is y equals 75 times e to the x over 150 plus e to the negative x over 150. So we know that any cables hung between poles take the shape of this catenary, and so because we know this formula, we basically need to know how long is the cable that's going to be hung between the two towers. Okay, so let's draw a little picture here. Okay, so we're just going to graph this in our calculator so that we can see what it would look like. We get y equals 75 times e to the power of x over 150 plus e to the power of negative x over 150. We're going to zoom out here. Okay, so here you can see what the graph is going to look like. And notice, if we want this to be equal, it looks like it's symmetrical along the axis. So I'm just going to add in our towers here. We probably get x equals negative 100. And we probably also get x equals positive 100. So essentially what we're trying to do here is find the length of the cable between the two towers. And here are the two towers right here. So the first thing we need to do is find y prime, which is just going to be 75 times. And recall that the derivative of e to the u equals e to the u du. So here we're just going to get e to the x over 150 and then times the derivative of x over 150. So this will just be divided by 150. And then plus e to the negative x over 150 divided by negative 150. And if we distribute that 75 in there, goes in evenly to 150. So we can just clean this up a little bit. So y equals e to the x over 50 minus e to the negative x over 50, all divided by 2. And that is y prime right there. Okay, so now we can find the arc length, or the length of that cable. So S is going to equal the definite integral. Well, looking at our graph, it looks like we're going from negative 100 up to 100. And this is going to be the square root of 1 plus, well, y prime, so e to the x over 50 minus e to the negative x over 50 over 2, and that is squared with respect to x. And when you plug this into your calculator, you're going to get 215.147, and this is, let's see, 200 feet apart, so this cable is going to be also in feet. Alright, so a very practical application of the derivative as well as the integral to find the length of a curve.